Okay, welcome all to the tutorial session. Share my screen. I hope you can see the screen. Alright, so first question is the difference between line integral and the surface integral. Yeah, we have seen both the terms in the lectures. What is a line integral and what is surface integral? There is a difference, right? Somehow I'm listening to my own thoughts.
Just a minute about that.
Yeah.
Is it okay now?
Uh, there is some echo, but it's okay. At least I can hear you.
Okay. So, like the line integral is the integral along a curve.
Mm-hmm.
Like for example, if
Yeah.
we have a loop, something like that, if
Sorry,
it is a
loop.
line integral, it would be along the circumference of that.
Mm-hmm.
With the
Mm-hmm.
surface integral, we would find the surface area.
Right, right. Yeah, so it's all about suppose you have a surface, so and then line integral would be that over the boundary of the surface you want to integrate it, right? So that will be considered as a line integral when you will just consider the boundary of your surface. However, if you consider your surface and you are trying to integrate your function over the surface, that would give you line surface integral, right? So, and this is what we understand by geometrically, that this is how that one is the boundary one has to consider and another is the surface that you have to consider. If I write this as an integration form, what will be the exact difference? Like, how would I write it mathematically?
For a line, the domain form is different.
Yeah, so how would I write then? Suppose I want to write the integration form, then how, what would I write? Either one line integral or two line or triple integral or how? This is what I mean.
Line integral is a single integral.
Yeah, it
Integral
will
is
be
a double
single
integral.
integral, yeah. And then suppose you have, if you want to integrate over the curve C, this is how would you write? This is okay, right? This would be your line integral over the curve C. And if I ask you how to write the surface integral, then
That would be the double integral over the given surface.
yeah. Correct. So this is the basic difference that we have one side we have line integral which will be just over the curve, or you, if you want to relate these two things, then uh, I mean you can just go by the boundary of the surface and then you'll get a curve over it, and then therefore you can form a curve out of the surface by just by looking at the boundary of that surface. All right, so this is all. Another question: suppose we parameterize a surface by some parameterization with parameters u and v, then what is the surface integral of f under the parameterized surface? I should say it is the like integral over the surfaces. And surface I have just changed by some parameters. Then of course this integral would change, ds would change, f would change, and s would change by certain other region. So how would then integral will look like?
be replaced by
You want me to explain?
ds could be replaced by under root
Hmm?
of 1 plus del f del x whole square plus del f del y whole square whole into dx dy.
Can you repeat? ds would change by?
Under root hello,
Yeah, yeah.
am I audible?
Sorry, I am not able to hear you.
Hello,
Yeah, yeah.
hello.
Yeah, say it.
Can you hear me now?
Yeah, I can hear you.
Okay, this will be under root
Okay.
1 plus del f del x whole square
Mm-hmm.
plus del f del y whole square
Mm-hmm.
plus del f del z whole square.
Oh, there is a z also, I doubt. You
Uh,
have taken care of z, right?
yeah, okay, there will be no z. This whole thing multiplied by dx dy.
Okay. So this is what you are telling me, just exactly ds equal to, right? But I am reparameterizing it, right? By functions of u and v. This is no longer be x and y. I have certainly more. So I have to interpret everything in terms of u and v. You remember something with the, okay, just one thing. When you have, there is a difference. Okay, f, when we have f dot dr, so you remember we changed by parameterization to certain, let's say parameter is t. I just want to make sure that there is certain parameter. Your f would be changed by f of rt, and this would be changed by r prime t, and then dt. You remember, right? This thing.
Yeah.
So this has been changed by certain other parameter, but with the difference that there is r prime t. Hmm. Similarly, if I change my s by this, I'm changing my surface. Suppose z equal to fxy, where x, y, z, everything has been changed in terms of uv parameters. Then ds, of course, needs to be changed. And if you might have gone through the lectures, then you might have observed that this is certainly something to do with the surface now. You earlier, many of the things were independent of that, but now you have to do something with the surface. So suppose I just parameterize that r by r uv. Then if you remember, I will just take ru, or sir was writing phi u, let's say this was his parameterization, and ru will be just del r by del u, and similarly you have rv, which is del r by del v. Then we would just do ru cross product rv to get the normal vector to the surface, and then we will take the norm of it. So ds would actually change by norm of ru cross rv times du dv. So here one has to be careful all the time. Yeah, either you are looking at line integral or surface integral, or you are looking at the volume of certain surface. It's all about how would you change. Okay, it depends. So in this case, since it depends on the surface, so you have to look at how you parameterize your r, and then you have to look at the cross product and the norm of it. Um, are you able to follow?
Yeah.
Okay. So then I would just say that your integral would be, so in this case question was to change this integral, right? So I would say that it will change to integration fxy z ds over the surfaces. It would change to f of your ruv, I will just simply write that, times your norm of ru cross rv times du dv. And of course that domain is that domain of parameterization. This is like parameterized domain. Yeah, we will see this how these things will be there if we look at certain examples. But I just want to make sure that you get used to this transformation, because then only we can compute the integrals over surfaces, right?
Yeah.
Okay, so this is fine. Okay, now we have surface integral. We want to compute the surface integral. For the function over the surface, let's say if surface is only a constant surface for us, 5. And over the surface is this where we have parameterized it. So now we should be able to change this integral into parameterized integral. Yeah.
Yeah.
So can you try doing this just by the way we just discussed?
Okay, then we have the function representation for R of UV. We
Mm-hmm.
will apply the above functions on that one, right? The phi u cross phi v and the norm of that.
Mm-hmm. Uh, just a moment. So you remember what was RU? What is that?
It is del R by del U.
Yeah, this is nothing but this. You know this how to compute. Hmm? Same thing
Yeah.
if I ask you, you can compute this also.
Hmm.
And in this case, what is your f? Yeah, what is your f, x, y, z, let's say? I will write capital F. You're integrating certain function on the surface, right? What is that function? It's like f
Yes,
dot
phi.
d. It's 5, constant function 5, right? So we don't have to change your function because parameterization will not change it. So your function will remain same. So now if you remember, we are trying to compute this f dot ds over the surface S, and this would be, if you recall, just now we discussed, it will be f uv, I should say r uv, and then ds is nothing but ru cross rv, and then its norm times tu dv. Of course, now the region has been changed. Yeah, following this, can you now do this? Hmm. Okay, let's look at the domain first. What is the domain here? It's like you are in the UV plane. So let me just write, this is my U, this is my V. So V is from 0 to U. Hmm? Can we
Yeah.
draw this? Yeah. Hmm. It's equality. So we have a domain where we have V equal to 0. V equal to 0 is your U axis. If you have v equal to u, it is a line passing through the origin, right? So u have this v equal to u, and then u has a bound. U is from 0 to 2 only. Yeah, so I think this is the region. U is from 0 to 2. Yeah, here is the region that you have to take care. This is your domain. Okay, now can we do something over here? What is RU cross RV, by the way? Let's compute that.
This 2u.
Sorry?
This will be 2u.
It just to you? That's all?
Yeah.
I have a
Like the
doubt.
I cap and j cap values are 0.
Okay, let me see. So RU is nothing but 1, 2u and 0. 1, 2u and 0. This is okay, right? Your RV means you have to partial differentiate your vector by V. Your first component does not have V, it will be 0. Second component does not have V. Last component has V1. Is that okay?
Yeah.
Okay, so now I cap will be 2u times minus j cap would be 1 time, and then there is no k cap. That's all. So your vector is 2u comma minus 1 comma 0. This is your RU cross RV. Is that okay?
Yeah.
All right. So now if we try computing the norm of it, what that would be?
The root of 4u square plus 1.
Yeah, it's 1 plus 4u square. So there is a slight difference is what you were saying earlier. Okay. So we have integration 5 times your norm. Norm was at 1 plus 4 times u square. And then du dv is the area of the region. Your region is D, and D we just saw. I'll just draw it over here again. Oh, no, this was the region. It's from 0 to 2, and this is your V, and this is your U, and this is line V plus U. All right, so can we see this? What will be? Can you solve it and tell me quickly what that would be? Okay, let's write the limits first. I'll write dv first and du first, du later. We okay. This region which we have seen, I think there are several ways to see this. It's a region of type 1 as well as type 2. So we will see it in this way. I will go from V. So V is from 0 to U. If I just draw parallel lines to the V axis is my looks like Y axis. It will cut at the first point at V equal to 0. And the last part it cuts is V equal to U. Yeah, so the limits will be from 0 to U. Is that okay?
Yeah.
And U region is from 0 to 2. So you'll just simply say 0 to 2. Now can we compute it?
Till this part it was okay.
Yeah, this is okay. So let's do this. Now, since there is no variable in our function, so it will be integration. It can be taken outside. I will just simply write this way. 1 plus 4 times u square, and then integration over 0 to u dv, and then I will write du. This is okay, right?
Yeah.
5 times this would be, so this integration is just mod v from 0 to u. Yeah, so
Yeah.
0 to 2, 1 plus 4 u square, and times u, and then du. Yeah, this should be okay. And now this can be done now. This can be done.
Yeah, I got it how to do this. Is it 5 by 4?
Uh, I think this 5 by 4, I'm a bit doubtful. Okay, let's do it. Maybe certain computational mistake. You know, you can simply put 1 plus 4u squared by some t, and therefore your 8u du will be just dt. And you can replace u du as dt by 8. Yeah, I think it is okay, right?
Yeah.
So I will write 5 by 8 and then u du is just dt to me, and then I will write this whole term as root t. But of course, limits will be changed now. If you have u to be 0, what is t?
If u is 0, t would be 1.
Yeah. And if you have u to be t and 2, then t will be
17.
17. Limits from 1 to 17. Yeah, limits will be changed. 5 by 8, and then you know the integration of t power half. Yeah. What is that?
T to the power 3 by 2 into 2 by 3.
Yeah. And then limits is from 1 to 17. So finally we got 5 by 8 times 2 by 3. 17 power 3 by 2 minus 1. Yeah. So I would
Yeah.
just write that. Yeah. So this is the answer. 5 by 12 and then 17 power 3 by 2 minus 1. Okay, so this is how we will compute this integral over the surface. So what we exactly did, so as we sir has been keep saying all the time that most of the time function may not be written in terms of a graph of a function. The surface is like so much mixed up, so you might not be able to write as a graph of certain function, but you can parameterize and then you can you can see the domain very simply, right? This domain is very simple to see and very simple to integrate over. So this is why parameterization is quite helpful. Okay, so we need to compute another surface integral, and surface is the cylinder of formed by this circle with radius 1 and height 3. So it's like this. To have circle, I am not very good at drawing, but yeah, it's like some kind of circle, and then you are trying to take a height of this is your height 3, I guess. Yeah. So this is how you are making your cylinder, and this is what we are interested in. Okay, so this is the surface that we have, and we want to integrate this function x plus y square over the surface. So directly we know that we can compute, of course, but is it better if we can change it into some parameterization and that can help us? Can we do that? I mean, usually whenever the circle comes, we have a standard parameterization. You remember?
Yeah.
Yeah, what is that?
Polar coordinates.
Correct, polar coordinates. So I will simply go by polar coordinates. I will write x to be cos theta and y to be sine theta. And of course, we are looking at the complete circle, so theta would range from 0 to 2 pi. And I will not change z coordinates. Z itself is very simple looking. It's from 0 to 3. All right, so my parameterization is in terms of now theta and z, right? So, or maybe if you want, you can write z to be certain u, but I think that's very immaterial. I'm just writing the same thing. Then your r, which is nothing but r of x, y, z, I'm just writing that it will be r of theta comma u, or you can just simply write z also. I don't mind that. Is that okay? That all the coordinates what we have, any point on the surface, I'm just changing that point by a parameterization which has the parameters theta and z or u, whatever.
Yeah.
All right. So if that is the case, and we know how to integrate a function over the parameterized surface, can you write down certain thing? Now can we change the integral? So by parameterization, integral over the surface S x plus y square ds. Can I rewrite it with what we know? Yeah, in this case, our fxyz is nothing but, can you tell me what is fxyz?
X plus y square.
Yeah, it is just x plus y square. So since I'm parameterizing, the points will also be parameterized. So what? How would f of, let's say, r theta z look like? It will be cos theta.
Is it cos theta, r cos theta plus r square sine square theta.
And what is r over here?
R is 1.
Yeah, so we don't have to care about r. It is just cos theta plus sine square theta. Yeah, this is our f. But how, you remember how ds has changed? ds has changed to, yeah. So
Yeah.
in this case, my parameterization is theta comma z. I would write here theta comma z. Is that okay?
Hmm. Yeah.
Yeah. Okay. Now norm of, okay. Let's compute this r theta and z first. Just a moment. R is in this case is
Okay, just uh, can you go to the previous one?
sure.
Okay, since like r is equal to 1,
Mm-hmm.
so like x and y can be represented only in terms of theta.
Yeah.
That's how we have transformed function of
Mhm.
xyz into function of theta z, right?
Yeah. Yeah, for
Okay.
x, yeah, because we are writing, for me, x is now in terms of theta and z. Okay. But z, of course, z is, of course, is a variable to me. If you want to see as a parameter, you can just write z equal to u so that you will not get confused. So now every function, every parameter, x, y, and z is in terms of theta and u. Or you can simply say theta and z. The same thing.
Yeah.
So now we have two factors, theta and z. So I have to take the partial derivative with respect to theta and z. So this is my sine theta j cap plus z k cap. So if I write r theta, what that would be, and what is r z? If I just differentiate with respect to theta, what would it give me?
Minus sine theta I cap
Yeah.
plus cos theta j cap
Mm-hmm.
plus 0 k cap.
Correct. And here,
0 I cap plus 0 j cap plus k cap.
correct. Now can we write what is the cross product for this?
Yeah.
Okay, let's write. Yeah. Okay, finally it would give me,
You get cos theta I cap minus a plus sine theta j cap.
okay, just a moment. Yeah, that's all. Yeah, very well. So, what would we get now if we want norm, right? So norm of r theta cross rz, what, there's a simple, what is that?
You'll get 1.
Yeah, it's just 1. Okay, so the integration would now change to, let's look at what we had. It is cos theta plus sin theta times ds, and ds has been changed to this times d theta dz. Yeah, this is our parameters, theta and z.
Yeah.
Earlier it was du dv. So it is cos theta plus sine square theta d theta and dz. Now one has to be careful about the limits. So the limits, what were the limits? This is one limit and this is the other limit. Theta from 0 to 2 pi and z from 0 to 3. Yeah, what is this? Can you compute it? I think you have to change a bit this one.
You have to change it to sine cos 2 theta.
Yeah, you're right. So it will be 1 minus cos 2 theta by 2. Yeah, so it would become 0 to 5, 0 to 3, theta cos 2 theta by 2. That's it. Integration of cos is just sine, right? Then we have 1 by 2 constant. That integration would be theta by 2. Then minus sine 2 theta by, then integration of this 2 theta, and that means you have to divide by 2. I'll get 4. 0 to 2 pi, and then integration from 0 to 3 dz. Is this okay?
Yeah.
Okay, it would give me sine 2 pi is
0.
0, sine 0 is 0. So I would just get, I think, 2 pi by 2. I think this is all. Yeah. 0 to 3 and then dz, and this would give me pi times z, and z is from 0 to 3. It would give me 3 pi. Yeah, so this is the integral over the surface for this function f. Yeah, so the value is nothing but 3 pi. All right, so I think now you know what needs to be done when it comes to surface integral, right? You have to be careful with the parameters, and you have to be careful with this kind of change. The small change of this surface area is nothing but the small change here, which will reflect with this kind of normal vector to that, and you have to take the norm of that. Yeah. Okay, here is some different kind of question. As you know, I just want to recall something. Okay, let me just recall something. Yeah. When we had line integral over f dot dr over c, let's say, and of course it had some kind of, if I have, let's say, this curve, and I'm trying to find this f dot dr over this curve. Okay, of course there is certain domain where I'm just looking at this curve. Then I have this kind of parameterization which has certain direction. Do you remember that? Suppose I'm parameterizing this rectangle. Okay, I have this rectangle. It's a unit rectangle. Okay. I'm parameterizing from this direction, this direction, this direction, and I'm getting back. And I'm computing the integral, let's say f dot dr, and over the c, this is c1, c2, c3, c4. Sum over ci's. I will just write this. Yeah, of course it will be like 4 integrals, each over c1, c2, c3, c4. Do you remember if I just change the I start writing parameterization in this direction, then I'll go this direction, then I'll go this, and then I'll come back. Of course, I can trace my curve like this also. And the other direction is, let's say, Ci prime. And integration is over f dot dr, and then we are summing over Ci prime. Do you remember what was the relation between these two?
It would be the sign would change for the answer.
Exactly. So the magnitude is not going to change for an integral, but it depends on what direction you are trying to move. And this is why there is a slight change, and therefore you get the equality, but with a minus sign. Same thing is here, and this was, if you remember, this was nothing but the geometrically the meaning was the walk done in certain direction. And of course, if I change the direction, then there is a minus sign just to ensure that you are working in the opposite direction. Sorry, what did I do? Huh. Here again, I want to parameterize a cylinder, of course, and I have to give certain kind of orientation to it. If you remember, orientation is always given. Sir has given certain ideas that suppose you have this surface and you have to define some kind of orientation to it, and you want to integrate certain uh, if let's say f dot ds over the surfaces. So he said that he wants to always keep his direction in the left of, he want to make sure that he's always left to the surface. Yeah, for that he chose the direction to be anti-clockwise. Yeah, this is anti-clockwise. Yeah. So same thing here. I want to give certain kind of orientation, and the way he gave orientation is by choosing a normal vector. So he says there are two kinds of normal vector to the surface, either this one or this one. Of course, this is minus n cap. Yeah. So and if you remember carefully, then this n cap. Suppose you have certain, let's say you have certain element over the surface which I am writing to be r x y z. Hmm? Then yeah, then and we parameterize the surface. Okay, we parameterize the surface by, let's say, x equal to x uv, y equals to y uv, and z equal to z uv. If you remember, then we did that. If you write the ru cross rv, this is a normal vector. This is always a normal vector. Yeah, because cross product always tell me that this vector is going to be normal to that surface wherever you are talking about. But since we are working over the unit normal vector, we will simply divide this by ru cross rv norm. This norm will make sure that it is a norm 1 vector. So basically, this is nothing but the normal unit vector to the surface which has been parameterized now. Yeah, I think these notations, are you following? I think he was writing phi u, I guess. Phi
Yeah.
u cross phi v, and then norm of phi u cross phi v. Okay, so whenever you want to make sure that you want to give certain direction, it is all about choosing the normal vector, because which way you are moving, if you remember correctly, I'll just tell you one more thing. If you have this one vector v with another vector w, if you are moving from v to w, yeah, then you will get a normal vector in another direction, and if you move from this to this, then you will get a vector in another direction. If you remember the thumb rule I told in the beginning, if you move from v to w, it will be pointing outward, it will be towards outward, and if you're going from w to v, it will be towards inward. I somehow can't show you here. Sorry.
We also visualize it using the screw.
Yeah, he just said in the beginning by screw and bottle, everything he showed. So it is the directions or orientations are always being measured with the help of the normal vector, because which way you are moving, it will be helpful once you know what is the normal vector to it. If it is pointing downwards, you are moving in the clockwise direction, and if you are moving anti-clockwise direction, then it should be going upward. If you can simply use your right hand thumb rule and you curl your fingers in such a way that you are moving from right to left, that means you are moving clockwise. You see, your thumb will point you towards yourself. But if you just hold your fingers in, I should say, you just put your thumb down and curl your finger from right to left. That means you are moving from clockwise direction. Your thumb will be inside. It will be pointing in the opposite direction to you. So the orientations are always being fixed by the normal vector. This is what I want to say here. Is that okay?
Yeah.
All right. So this is what I want to say here. I hope you understood. We want to give an orientation to the cylinder. So we want to give means we want to find a normal vector. And question is how to find that? And answer is we know that, because if we parameterize certain points, certain surfaces, I know how to find it. This is what we know. We take the vector which is having by partial derivatives. This like a tangent in the u direction, tangent in the v direction. You take the cross product, it will be the normal. It will be like the perpendicular to your surface. And then you are dividing just to make sure it is norm 1. Okay, so far so good. So we know what is how to find a norm 1 vector which is perpendicular to the surface. Let's come back to the surface that we have. We have the cylinder, and the question is about parameterizing it. Can we do it? Okay, you need some help, right?
Yeah.
Okay. Surface is, you know what, we are giving orientation to a cylinder. So let's just roughly draw it. I have drawn it, but let's just draw once again. I'm very bad at drawing, but forgive me for that. Okay. You know, each circle that is in the cylinder, it has been formed by certain all circles, and having all circles have the same equation, x square plus y square equal to what was the radius? It is general r square. Okay. I know the height is nothing but 3. That I know. I know. So, of course, since we know things about parameterization, why won't we parameterize it? So, what will the obvious parameterization? Because the surface is in terms of, like, you have r equal to r x y z, where you know that what is the relation? It is x square plus y square equal to r square, and z is from 0 to 3. So the obvious parameterization is like x equal to r cos theta, y is r sin theta. Yeah, this is okay, right?
Yeah.
And now you know that how to find this normal vector. So the normal vector actually gives you the orientation. And if you just take the negative of this, it will give you the another orientation. Yeah, there will be two orientation based on which direction you are following. So this n cap which we are writing by ru cross rv, by norm of ru cross rv, it is actually in the upward direction. I mean, it will make sure that it is like outward orientation to the cylinder. Outward meaning, if you remember on the surface, if we are giving this kind of orientation, we are in the left of, or maybe we are outside this. We are outside this surface. But if I give orientation in the reverse way, then we are inside the surface. So this direction will be outward. This is what I want to know. And if you want inward, you just take minus of n cap. This will be inward direction. Okay, so the orientation we want to give is by finding this RU, RV, and we can do this. So just let me make sure that you see everything on the page. Yeah. So RU cross RV is nothing but I cap, J cap, K cap, and oh, sorry, U here. U and V are nothing but R and theta. Is that okay? Uh, hello.
Hello.
Yeah. Can you hear me?
Yes, I can hear you.
Okay, so here parameterization is only for theta and z. I think you can see because r is anyway fixed to us. It is theta which we have to make sure that, so theta is the one parameterization and z is another parameterization. So here u and v are nothing but theta and z. So I would simply take the theta, r theta, which would be minus r sine theta, the first one. J cap will be r cos theta, and for z there is no parameterization in theta, so it is 0. X do not have any component with z, so rz first component is 0. Same with y, z will be 1. Is this okay?
Yeah.
All right, so we got r theta cross rz b minus r sine, just a minute, r cos theta I cap plus r sine theta j cap. This is enough, right? That's all. Yeah. And 0 k cap. Therefore, your normal vector or the direction you want to make sure is nothing but r cos theta, r sin theta, comma 0, and the norm of it, which will be just r. R. And therefore, you will get cos theta, sin theta, 0. Let's look at the meaning. Let's look at the meaning. This would mean that suppose you have a circular region. Actually, you are looking only at circles, right? Although it looks like cylinder to you, but we are all the time moving a circular region, right? So you want to cover up this surface, but how are you moving on the surface? You are actually moving on the circular path, right? So if I just look at theta equal to 0, cos theta is 1, sin theta is 0, so point will be 1, 0, 0. So that means you are starting from 1, 0. That means your direction is this, right? That this is how you have to see that your direction is anti-clockwise and therefore you are outside the surface. That means you are pointing outward to the surface. If it would be in like clockwise direction, that means you are pointing towards inside the surface. You're pointing inward inside, meaning the direction of your normal vector, and that you can think by looking at your thumb. If you are moving, let's say clockwise direction, that means your thumb is towards inside. You are pointing towards inside. When you have your thumb towards yourself, that means you are actually pointing outwards to the surface.
Yeah,
Does it make sense?
it does.
Okay, I mean, it's very hard to explain, but I hope you understood some part of it. All right. So if somebody wants you to find any orientation, then this is how you will orient. You will orient your surface just by
The orientation just means the n cap vector.
exactly. That's all. That's all. All right. I hope this makes sense. Then yeah. Question 6. Um, okay, this is the same notations I think I am trying to write. Here I want to write 5. We parameterize the surface by UV, and this equality we know, right? This we know. ds would change to norm of the cross product times the area over the parameterized domain. This we have been doing, right? Hello?
Just a minute.
Uh-huh. Let's just go back, okay? If you are a bit confused, then here, look at this line. It is the cross product of parameterized surfaces times the area. This is dA.
Yeah.
Let's look there. This is the parameterized surface, the cross product, its norm, then area. Yeah, this we know that if you want to compute the integral over a surface, this is how it will be parameterized. Hmm? Now
Yeah.
we also know that n would look like this. N is the normal vector. Yeah. Suppose I want to relate these two things. Can I relate? One is f dot ds, ds is a vector. Another is f dot n dot ds, this is magnitude only. This is the surface area. You know, Servo is also pointing out that surface area has some kind of direction, hmm? Which he was writing area vector. It's like that only. I'm just talking about here the magnitude of the area of the surface, and this is nothing but the surface with the vector. And you know, this parameterization, you know, I have written that. And you know, can you relate these two quantities? I think we can. Just think for a moment, everything is written here itself.
Yes. Um,
Mm-hmm.
if you just try to substitute
Yeah,
things,
let's do it. Yeah, let's just do it. This one, it is integral over domain f of phi, let's say uv, and then norm phi u cross phi v du dv. And this is nothing but f dot phi u cross phi v, it's a vector, by norm phi u cross phi v du dv. Sorry, I'm sorry. ds has certain meaning, right? That is nothing but norm of phi u cross phi v times du dt. Is that okay? Can we parameterize? ds would go to norm phi u cross phi v times du dt. Yeah.
yeah,
So it's in the product. So this get cancelled, and you will be just left with f dot phi u cross phi v times du dv. So now you can see, right, how to relate these two things.
yeah, one of them looks like the scalar variation of line integral.
Yeah, I mean, I'm just taking the normal
You just
vector to
put it
it.
there. Like,
Yeah, yeah, that's all. I
and
mean, more
the
or less,
second
there's
one will be in terms of a vector.
right, that's all. Okay, I mean, it's not much. I just want to make sure that there is a some kind of a relation, and that's all. I mean, it doesn't give you much, but anyway. Okay, so let's just compute the surface integral. I would just say that uh, what I want to say is just a moment. Am I getting confused with certain thing? Yeah, hold on a minute, okay? I just want to clear something. I just want I make sure that nothing I will tell you wrong. Okay. Yeah. So you know what was the point here is this. Uh, if I say that you have a surface with orientation with unit normal vector, yeah, with
Yeah.
unit normal vector, then can we say something? It's unit normal vector.
But like if n is a unit normal vector,
Mm-hmm.
then in both the cases magnitude will be the same. Just
Yeah.
the direction of the final vector will be different.
Right. Right. So, you know, what I just want to point out here is that you don't have to even cancel this, and this will be your f dot nds. Your f dot nds is simply this much only, and which you can just simply by, of course, this is vector, this is a vector, dot product makes sense. And you can find the area that has certain meaning to it. This has no issue. So as long as your function is a scalar field, this also has a meaning, right? Because this is a scalar, this is a scalar field, and then du dv, this has a meaning. So as long as your f is a scalar field, that means it is from like Rn to R, it has a meaning and it makes sense. And here in this case, if f is a vector and then you are taking the cross product, these two things has a meaning. You can take the dot product of two vectors and it has a meaning. Yeah, this is all I want to. I think I don't want to confuse you. Let's just leave this part, okay? Yeah, just leave. I think you know what I mean to say here, that f dot ds is simply that vector, and that vector has certain relation with your normal vector. That's all. Like
Yeah.
these two things are related just by a normal vector. That's all. Okay, suppose we want to find this. Now we know that how to find this normal vector to the surface S, which is being parameterized by our UV. UV has a bound which we have given. Can you just try computing this? Okay, let's do it together. By definition, f dot nds is nothing but mm, f of, we saw, right, f of ruv. This is how f would translate. N is nothing but ru cross rv. Why? It's norm. Yeah.
Yeah.
And ds, I know it has to be multiplied by norm of the cross product and then du dv. Yeah. This would get cancelled, and anyway, if I want to compute this, You here see one thing. Earlier we were okay. Let me just go back. Just go back. All the time your surfaces, if you see, your function values were scalar field. Let's go to another question. Scalar field. You observe this, right?
Hmm.
Okay. Anywhere else? No. But in this question, look at this. It's a vector field. Yeah. So,
Yeah.
this kind of quantity is called actually flux. So, this we call as flux integral. Earlier, if you had just f dot ds over the surface s, it is just integral over, it does not have any physical meaning. It is like integral over surface s. Okay, but this, suppose your f is a scalar field here. But if your f is vector field, this has certain thing with physics. We call it as flux integral. This is how we compute flux. I don't know much about this, so I'll just give a name flux. That's all. Okay. So here the computation is like f of RUV times RU cross RV. Earlier, just let me point out one more thing. Earlier f was field, scalar field. Then we were taking the norm of this because this is a vector. How would I take the dot product of, even if I get a dot product, I will get a vector only, right? But integration of a vector over a certain surface, we don't know how to do that. So in this case,
Just
this is
repeat
how,
what your last said.
yeah, so I said there are two things to notice here. Earlier, which we were computing all the time, the integral over the surfaces, f was scalar field. And when we parameterize, then we got this f of RUV, and then we got norm of RU cross RV, du dv. You see, this case is different. This is when you have RU cross RV. Okay, you have RU cross RV, not the norm, because in this case your function is a vector. This is also a vector. Dot product gives you scalar. There you can evaluate your integral. Is that okay? Hello?
Hello.
Yeah, can you, are you able to follow?
Yeah, I could follow.
All right. So, yeah, that's all I want to say. So, let's compute this now. These are certain side remarks. So, what we have to compute is this part, RUV dot product RU cross RV times du dv over the region D. Now, you have given the region, you have given the parameterization. Can you do this now? Your f is given to you.
Yeah.
XY has been given to you. How to change that? And there is no Z, there is no K cap for F. You can just simply write 0 dot K cap.
Yeah, when one term is missing, we just write 0.
Sorry.
Yeah, like for f, it is represented just as minus 5 comma x. There's no third term, so we'll just take it as 0.
Right, right. All the time, let me just tell you once more. This parameterization is like for any r which is r of x comma y comma z. That meaning is x is u for u, y is v square minus u, and then z is u plus v for us. This is how when one needs to see the parameterization. Uh, Assuming this, you know how to write f with respect to this parameterization. Write it. What would be f then after changing x and y? Can you tell me? F of
F would be u minus v square, comma
mm-hmm.
u, comma 0.
Yeah. So this would be your first FRUV. Can we compute RU cross RV? Let's just look at once again what is R. RUV is UI cap, V square minus U. I'll just copy and I'll do it on the next page.
The dot product is giving a 0.
Is that so? I don't think so. Let's just check again. RU is the pen. RU, what is that
I
for
think
you?
I messed up again.
Maybe take some time while computation because you might be doing fast and then making mistakes. Is this okay? Are you getting the same?
Cross product should be 2b minus 1
Just a
plus
moment.
product.
Is that what you are getting?
Yeah.
Just a moment. No, I did something wrong with this. I cap is wrong. Yeah, this is correct. So I'll just write the vector RU cross RV is nothing but minus 1 minus 2V minus 1 2V. Is that okay?
Yeah, it's okay.
All right, so let's go back. F dot F of RUV and then dot product RU cross RV du dv over the region D. So f of RUV we had is u minus v square I cap. I'll just write that. U minus v square I cap and u j cap plus 0 k cap, and this cross product is times minus 1 minus 2v I cap minus j cap 2v k cap times du dv. And we know the region. U is from 0 to 3, V is from 0 to 4. Yeah. Can you do it?
Yeah.
Okay, I'll leave the computations. Answer is 340. Shall we go ahead? Or
Yeah.
you want to compute?
Let's go ahead.
Okay. Okay, the next question is about Green's theorem. Yeah, so what is Green's theorem and does it serve any purpose? So far we are doing, okay, we have been doing finding area under the surface, we have been finding volume under the surface, sorry, area under the curve, volume under the surface, and we are integrating a function over a surface, and then we are integrating a function over a scalar field over a line integral over a curve. So far we have been doing all this. Okay. Naturally, one would ask that can we relate one of the stuff with the other stuff? Can we relate one of the, just like you remember single integral f of xy dx, let's say, sorry, fx dx from x1 to x2. I would write it this way: dy dx 0 to fx x1 to x2. Is that okay?
Yeah.
This would mean that I'm finding the integral of f over the curve over the integral x1 to x2. But this would mean it is the area under the curve f. So it's like similar thing I want to ask here. Green's theorem is one kind of theorem which connects two things. If you remember correctly, you can tell something. Sometimes finding the surfaces or the integral over the surface or integral of f over a curve is sometimes difficult. But if we know that finding line integral can be changed to surface integral or surface can be changed to line integral, like that if we can do, then maybe sometime we can skip the difficulties and we can go to other way and we can solve there. And this is most of the time we try to do. When we do not know one thing, we try to find a substitute of that. Just like we do not know suppose we do not know how to prove a continuity of a function by definition, epsilon delta. I will write a characterization. Characterization says if your sequence goes to some number, f of that sequence also goes to that number. That means I found a substitute of proving the same thing by different way. Yeah.
Yeah.
This is all I want to ask here, that sometimes we do not know how to compute, let's say, line integral, but maybe we can compute surface integral and the vice versa. Okay, so yeah, let me just, without any further delay, I'll just tell what is this meaning. Yeah, so Green's theorem. Suppose we have R is a region in R2. And let me just draw also. You have this region, R. It has a boundary, right? I'll just write dr, del R. This is the boundary, right? I will simply write that to be as a curve C. So C is the curve for the region R. And let my function is, this time my function is a vector function, vector value. Pxy, cap, qxy, j cap. Certain function depending on x, certain function depending on x and y. And it has to be defined on, of course, in the region, otherwise there is no meaning. So defined on R and C both. Then this is what the statement is. Integral f dot dr over the curve C is double integral over the region R del q by del x minus del p by del y over the region R. This is the area of the region R, where C is, there is a convention which sir has been following, that we will parameterize, I should say, we will parameterize the region such that region is always left to the curve. Region is left to the curve. This is how one of the convention we follow. Okay, I have written a statement. Let's just give some time to the statement. One side we have this kind of line integral, if you see carefully, and other side we have this surface integral, if you see carefully. So Green's theorem says one can relate the line integral around a closed curve, let's say. We can relate with that with the double integral over a region inside that curve. Does it make sense?
Yeah.
Yeah, so the Green's theorem is all about, you can sometime, even you do not know how to find the line integral, you can just simply use the Green's theorem and go to surface integral, double integrals, and do things if you can do it. All right, let's just use this to find certain things. Let's come. We want to evaluate this f. You see here f dot dr. It's a f is nothing but x square plus y square comma 2x. So it's a vector field, right? And whenever you have vector field, f dot dr would mean it is like work done, right? If you remember, when you have f dot dr where f is a vector field, then this is nothing but the work done. Work done along the curve C. So this was recall. So same thing, we are again in the same scenario. We have f dot dr over the curve C over certain region. Yeah.
Yeah.
Can you use Green's theorem to do it? You know, let me just go to the region. Let's just draw the region first. Can we draw the region first? Can you help me in drawing it? It's just on R2 plane. It is like x-axis, y-axis. You have to draw, that's all here. Y is from one curve to another curve. Can you draw y equal to 2x square?
Okay, 2x square, it's like the quadratic curve but steeper.
Yeah. So I'll just draw like that. Of course, it's even more. I should draw it more carefully. Oh, I'm sorry. Yeah, I should be drawing like this. More like this. Even this is also not perfect, but anyway, let's not worry about that. Y equal to 2x. If you see carefully, y equal to 2x would be something like this. So I'll just draw, this is y equal to 2x. This is y equal to x square. Your region is in between. Yeah. So you
Yeah.
start with x square and you approach till this. This is how your region is. Yeah. This is your line parallel to y axis. Your region is starting from x square. You have to go to y equal to. Starting from x square, you have to go to this. So this is all. That's all your region is. But of course, your limits of x has to be fixed. So you are from just 0 to 1. Therefore, this has to be 2. All right. So this point of intersection is 1, 2. Fine, we know the region. Now, what I want to say here is you have to parameterize this. Suppose you want to find f dot dr by simply finding f dot dr over the curve C without going to Green's theorem. The meaning is you have to parameterize this curve. Curve means you have to go, you have this region and you have to parameterize. I'll just try to show you where to. You start from, suppose here, you parameterize it and then you have to go and then you have to come back here. You understand this?
Yeah.
And you have to cover the boundary, that's all. But when you go to double integrals, you are in the region. So I'm saying here, since you know the region very well, you have parameterized the region, right? You know the limits of the region. Let's use the Green's theorem then. Does it make sense?
Yeah.
Okay, so let's just use what is the Green's theorem. Your function should be p and q, and then you have to take the partial derivative of q and then p with respect to x and y. So what is our p for us? So our f is x square plus y square I cap plus 2xy j cap. What is our P? What is our Q?
P is x squared plus y squared.
Yeah, this is a function of x and y. Again, this is function of x and y. And the formula says that it would be del q by del x minus del p by del y, and then area of the region, dx dy over the region R. Now, can you compute and tell me what is this?
Del q by del x is 2y. And
Yeah, it's 2y.
del p by del y, del p by del y would be 2y.
Yeah, it is 2y. So the answer is
0.
0. Yeah, this is why I wanted you to
Just an
compute this.
observation.
Mm-hmm.
See, these types of notations are there in differential equations while we are dealing with exactness of a solution.
Exactly, exactly. Del p by del, just a moment. When you have y dy equal to p, just am I confusing something? No. We have p dx
When,
plus q
when we
dy.
have, yeah, if del p by del y equals to del q by del x, then it's an exact solution.
Yeah, and then you know how to solve this differential equation, right?
This one is an exact solution. This one in the
Yeah,
question.
right, right. But somehow it doesn't have anything to do with that. But yeah, notations are similar. Yeah. Yeah, so here, kind of there is no work done then. If somebody wants to know, somebody wants to check what is the work done of this by applying this force over the curve of this region. And somebody will ask, what is the work done? Yeah. Um, you have certain options. Then, by parameterizing the curve, and then you have to find the line integral. It's lot to do. But when you apply Green's theorem, nothing much to do, right?
Also, the
So,
zero work does make sense because like, we are returning to the same place after traveling.
uh-huh. It's kind no displacement. Is that what you want to say?
Yeah.
Well, kind of one can say. I am not sure. I mean, how to say that, but maybe, yeah, maybe you're right. I'm not pretty sure about that, but yeah, this is one of the intuition that since we are coming back, so there is no work done. But of course, even if we are coming back, there should be some displacement. If there is a displacement happening, there is a work done, right? Because when we are moving through a closed curve, we come back right at the same place, but it does not mean that we did not do any work. Yeah, but maybe there is some other logic, but yeah. Okay, so I think you understood what I want to say over here. All right, so let's do one more question on this. Calculate the line integral where C is the rectangle with vertices oriented counterclockwise. Again, it's again f dot dr. Whenever something comes to you, looks like line integral, you have options. You should think at this very same moment. You should start thinking in this way. Do you want to parameterize the curve, or do you want to see the region? If see region is very well enough and you can see the region, you can parameterize the region, and then you can change from the single integral to double integrals using Green's theorem. You have to decide. Okay. So, what do you want to do? I would rather go by double integrals, and I will tell you why.
Okay.
Let's draw the region. Most of the time, it depends on the region. Let's draw the region. It's again, we are in the XY plane, so it can be, one can draw it. Just a moment.
Again, since it's a rectangle, we would like divide it into 4 integrals and solve them individually.
Right. This is why I don't want to do that. You have to make 4 curves, and for every curve, you have to find the line integral, and it's like lot to do. Yeah. So we have this 1, 1. It starts from 1, 1. 2, 3, 4, 1, 2, 3, 4, 5. Yeah. Another point is 4, 1. Another point is 4, 5. And then 1, 5. All right. So this is the region that we have over here. Of course, you can either go, but I'll just go by the region, because so which type do you want to divide or to see this region? Is it type 1 or type 2?
Type 2.
By 2 you mean y in terms of x, right? Or x in
Type 2
terms of y?
means x in terms of y.
Okay, okay, okay. Let's just write the next in terms of y. Then you have to draw line parallel to the x-axis. Okay. So I will draw like this,
Okay,
and then
since this is a rectangular domain, it will just
yeah,
take the end values
yeah.
for the limits.
That's all. So you are actually going from which line? This line is nothing but this is like x equal to 1.
X will go from 1 to 4.
Just a moment. Is it x equal to 1 or y equals to 1? This. Yeah, I can use that anyway. So it is like x equal to 1 to x equal to 4. And then y region is like, I'll just like this.
1 to 5.
Equal to 1 to x equal to 4. And then y equal to 1 to then y equal to 5. We are going this way. All right. So we have the region. It's good enough. And we want to find f dot dr. Yeah, f dot dr. So I will again use the Green's theorem. So use Green's theorem. I think I did not write last time. By Green's theorem. Yeah. What we got is integral del q by del x minus del p by del y, and then dx dy over the region R. This is my region R. Okay. My P is this, my Q is this. Can you quickly compute it?
Answer is 84.
Minus 84, exactly right. This time you did your computations well. Minus x square, I think this is 0. Dx dy, region is from 1 to 4, 1 to 5. This will be minus x cubed by 3, 1 to 4, and then dy is anyway 5 minus 1. I will simply write that. Minus 4 cubed minus 1 by 3 times 4. 464, yeah. Minus 64 plus 1, it is minus 63 by 3 times 21. Sorry, 4, which is minus 84. Yeah. Okay, I think, and it depends on the orientation. Since we had oriented in such a way that, moment, did we really oriented it? Yeah, you remember we followed this notation that in the Green's theorem itself, we are saying that the region has been parameterized to the left. And this region is also counterclockwise. Counterclockwise meaning the same direction, same orientation. If it would be like a different, if it's written like counterclockwise, then of course you have to write minus sign to the Green's theorem. Do you follow that?
Yeah.
Yeah, so I just want to make sure that direction is important. Okay.
Like by convention, this is how we do it with the Green's theorem.
Yeah, correct, correct. By convention, we just always use orientation to be counterclockwise. If somewhere it comes clockwise, you have to be careful with the sign. Yeah. Okay, here is another question. I think. Mm, okay, let's just do it. I think you know it because I just discussed this part a few minutes ago. Question is to find the work done by a force field over the circle exactly once in the counterclockwise direction, starting and ending point at 0, 2, 0. You tell me how would you do it?
I think I'll need help here.
Okay, you tell me where do you need help, then only I'll tell you.
Okay, to find the line integral, we need the function r.
Function R. Um, R. Sorry. We need f dot dr over c, right? This is the line integral, right? And the meaning, geometric meaning is work done by force F and along that the curve C. Is that okay?
Yeah.
So was that okay, or this is now okay? Now you understood this is how you have to done. You have to do.
Okay, we have to parameterize it and get the curve
Mm-hmm.
along which we have to move.
Just before some time back, I told you if you had issue with parameterization, you can do something else.
The Green's theorem.
Yeah, now you came to the point.
But how do we implement that in this one?
Okay, what does it say? You have to find the work done over the circular region. So your region is, your curve is this C, right? And
Yeah.
this is 2. You have x square plus y square equal to 4. And you are moving only once, exactly
Yeah.
once. Counterclockwise, the direction is also same. Starting and ending point is also 2, 0. It is the same. Counterclockwise means you have to parameterize this way. If you want to parameterize, it's a standard way to parameterize it. That means you are in the same line which we want, right?
Yeah.
But if you want to use Green's theorem, then your region would be entirely this. You have to, this time it is just the curve. But double integration would mean the region. Okay. Del q by del x minus del p by del y. Yeah, now can you do it? How would you parameterize it if the region is this? Like either you can find the area. Okay. Let's just you compute this. What is this first? I think that would tell you how what to do. Hmm? Just tell me what is this.
Okay, like we have the functions p and q involved here.
Mm-hmm. Isn't it this P and this Q?
That's what I was thinking.
This is our P, this is our Q, that's all.
In the differential form, we represent it as y plus sine x dx plus
That's all.
epsilon.
Exactly. You know, this line integral would mean that y plus sine x dx plus ey minus x dy. That's all. Over the curve. See.
So this function inside the integral would be minus 2 dx dy.
Exactly. Good. This is minus 2 and then region this dx dy. What is this meaning?
This is a rectangle.
Rectangle. R is, I told you R is this region.
Oh, okay.
What is the meaning? Double integral over R. Isn't it?
Yeah.
The area of the region R, right? Can you tell me area of the circle with radius 2? Isn't it pi r square?
Yeah.
You're taking so long to do that, right? Pi times r is 2, so it is 2 square, so it is minus 8 pi. So the final work done is nothing but minus 8 pi. You know, okay, just let me tell you one more thing. We started with 20, we came to 20. Looks like we did not do any work, but there is a work, right? So I don't think that kind of argument can
Like
help us
if
if
we
we.
had to manually do the integral,
Yeah.
then like y would have been from minus root of 2 just minus root of 4 minus x squared to root of 4 minus x squared, and x would be
Yeah.
from
Yeah. Let's write that. Minus of 4 minus x squared to 4 minus x squared.
x would be
And
from
your
minus
x is
2 to plus
from 0 to 2. And this is your dy dx, right?
minus 2 to plus 2 x.
No. Your limit of x is from. Okay. It's minus 2 to 2. Okay. Do I have to break the region or is this okay? Let me just see. We are going from minus 4x 4 minus x squared to 4 plus x squared, all right. All right, so let's just do it. Does it have some issue? Two times 4 minus x squared dx, then minus 2 to 2. Do you know the formula? I don't know the formula actually for this. A
Even I
minus
thought
x. There is a formula, root of a square minus x square dx. I don't know that formula.
it involves log and all.
It involves sine, I think. I am not sure, but you should be able to write it. If not, then let's just do it by let's just do by polar parameterization, polar coordinates. We have r dr d theta dx dy will change to r dr d theta. Radius is from 0 to 2. Theta is 0 to 2 pi. So you'll get r square by 2. And you know, there is a minus 2 over there. I am just writing that also. Minus 2 times this. Minus 2 times this. Minus 2 times r square by 2, 0 to 2, and then 0 to 2 pi. So minus 2 and then 4 by 2 and then 2 pi minus 8 pi. Is that okay? Is this okay?
Yes.
Yeah, I think it should be able to come. I don't know the formula, so I'll just skip. I go by polar coordinates. Yeah. Okay, here is, I think I will skip this question. I will skip this question. Area enclosed by an ellipse. I'll just say some things, okay, over here. I have to find, this is certain, let's say I have an ellipse. I want to find this area. By definition, it is the area over this region. Let's say if I'm writing this region R, it is just dx dy, right? You know, here there was something which I want to say. Okay, let's just do it. Let's just do it. We have some time. Area is this, area of the ellipse. Do you agree this? Area is nothing but this region which I have drawn, dx dy, double integral. Hello? Are you there?
Hello.
Yeah, yeah. Are you there?
Am I audible now?
Yeah, you are. You are.
Yeah, I was there.
Okay. So what do I do over here? I will just parameterize it by writing x equal to a cos t, pi to be b sin t, t from 0 to 2 pi. Does it make sense?
Yeah.
Okay. Now, just a moment. Suppose, okay, here I want to give you actually certain thing. How do I say that? If I don't know how to use that, but just a moment. I actually want to use Green's theorem, okay? But Green's theorem has to be used in such a way that you are actually computing f dot dr over a curve and you will land up inside del qy by del minus del p by del x and then dx dy or certain region. I actually want to relate those things here, and then how I'm relating is this. Suppose I give you one f. Suppose I give you one f. One f is nothing but minus y by 2 I cap plus x by 2 j cap. Yeah. Uh,
Okay, how did we get this one?
yeah, that's what I do not know how to convince you by saying that actually I want to do that, but mm, yeah. Okay, yeah, here is the way. What is del q by del y and what is del p by del x? This is my p. If you remember, this is my q. Tell me now.
Minus 1 by 2 and 1 by 2.
Yeah. So
No.
mhm.
Oh,
Minus 1 by 2.
oh no.
Uh,
The Q is x by 2, right?
q is x by 2. Yeah, yeah.
Then both will be 0 in this
Sorry,
case.
sorry. I changed certain things. I think this is x and this is y. I'm sorry. Yeah, yeah. I did something wrong. This should be okay now. This is half, right? This is half minus. Yeah, so del q by del x minus del p by del y is nothing but half plus half, it is 1. Yeah, just let me write what I want to say. Let me write it first. So double integral del q by del r x minus del p by del y dx dy over the region R is nothing but integral dx dy over the region R. Do you agree?
Yeah.
Yeah, because difference is just 1. This is nothing but the area
Hmm.
of ellipse. Do you agree that?
Yeah.
Okay. So what did I do finally? I chose a f such that work done over that by that force f along the curve given by the boundary of ellipse is exactly equal to the double integral, which is nothing but the area of the ellipse. You agree that?
Yeah.
Therefore, I can use now line integral to compute the area of the region. Do you agree?
Repeat the last statement.
Yeah, you know, I wanted to compute area of the ellipse. The way area is, it is double integration dx dy over r. It has nothing to do what I know from Green's theorem, but what I want to say, I am telling you that use Green's theorem to find the area. Okay, but Green's theorem is it will hold unless you have certain f which has a property that it should be a vector field and del q minus del x by minus del p by del y. As long as this is 1, then it will be just dx dy over r, and this is nothing but the area.
Yeah.
It is all about finding that f for which you can get the difference to be 1. And somehow I constructed one f
Okay.
for which the line integral is exactly equal to the area of the ellipse.
Okay.
So now we want to compute the area. And I don't want to use the parameterization there. But I will use the parameterization for the curve and I will go over the line integral. I'm going backwards. Usually we have to find line integral. I'll go to double integrals. This is the reverse way. Double integral I have to find. I will use the line integral. I guess you're following.
Yeah.
So we are in region f dot dr over the curve C, and f, if you remember, I have the way I have chosen is this. Yeah. So
Yeah.
by definition, it is minus y by 2 dx plus x by 2 dy over the curve C. And C I have to parameterize now. Yeah, C is this what I have to parameterize, and I have parameterized actually. I have written x to be a cos t, y a cos theta, y to be p sine theta, and the equation of ellipse was this. Yeah. If I parameterize this way, x is a cos theta, y is b sine theta. I would get x square by a square plus y square by b square equal to 1, right? This is fine.
Yeah.
And the theta is varying from 0 to 2 pi. So I am parameterizing my x and y only in one parameter, which is theta, and theta varies from 0 to 2 pi. Do you agree?
Yeah.
So I will just write 0 to 2 pi. My y is minus b by 2 sine theta. My x is a minus sine theta dx plus x is a cos theta by 2, and then dy is b cos theta. What would I get? There is a minus over here. I'll get ab cos square plus sine square by 2, 0 to 2 pi theta. Isn't it?
Hmm.
I'll get ab by 2 and then 2 pi. Just theta and 0 to 2 pi. ab by 2 times 2 pi. Pi ab is the area of the ellipse. Area of the ellipse pi ab. Does it make sense?
Yeah.
So, ellipse I should say. So let me just say one more time. Area, we were trying to compute area, and the way area has been written, it has nothing to do with the the Green's theorem, but we found one f for which I can relate the line integral with the double integral using Green's theorem, and then we computed the line integral in order to compute the area of the ellipse. So it's like going backwards. Yeah. All right, so far so fine. Okay, just give me a minute. I want to do one more thing and then I'll just wind up. Okay. For that, I will just stop recording for a minute and I'll sorry, not stop recording, stop presenting for a minute. I'll present again. Okay, I'll present again. Can you see in the screen?
Yeah.
Okay, here is one more thing that I want to discuss. Yeah. Till now, we have not yet. We have been writing that surface and area of the surface. I will tell you. Oh, there is one more question. Okay, I'll just say something over. Question is, the final question is, find the area of the surface of revolution. Surface of revolution obtained by rotating y equal to x square from 0 to b along x-axis. I'm rotating along x-axis. Okay, what is this figure that I want to tell you here? Suppose you have this curve y equal to fx that you can see in graph part A. There is a and B, two figures. So in first figure, we have this curve y equal to fx and we want to parameterize it. We want to parameterize the surface somehow by surface of revolution. Then what we want to say that I want to revolve this surface in such a way that I will keep the x coordinate same, but y and z coordinates has to be revolved along that fx. So I'm not going into the details, but if you see in the second diagram, you can compute this y coordinate as well as z coordinate by fixing x, because your y has to be computed in terms of x. Your y is a function of x. Limits has to be they have to be decided on x, and then further x will decide what y will be. Yeah. So then y has to be decided through x, therefore, and the angle, if you see here, there is an angle theta. Yeah, there is an angle theta, which if I just look at the fx, if I just drop the one point on the graph on the xy plane, then I will get the distance fx, which I'm writing here in the first graph, in the first image, let's say. Here, this angle is theta, which I'm calling here. and one can compute then points on the graph, of the curve, which is, let's say, xyz, by writing, by perpendicularly, by drawing this point xyz on the xy plane, and look at what are the coordinates. Yeah, it is all about, like, this is one point on the graph and I am just putting it perpendicular on the xy plane, and I will just look at what are the coordinates of that point. That coordinates has to be defined by, this is nothing but your fx sine theta, and this is nothing but your fx cos theta. This is how your y coordinate becomes fx cos theta, and the z coordinate, yeah, this is your z coordinate, this becomes your fx sine theta. I know it's a bit, I mean, you should give time to understand this, but what I'm telling is, once you want to parameterize a surface of a revolution, you can always parameterize it by fixing x and by fixing y and z in terms of f of x and the angle theta, of course, because you want to rotate it, so you have to rotate with certain angle. I mean, are you following bit of it at least?
Yeah, a bit of it.
Okay, so it is all about how will you write the parameterization of a surface of a revolution. Okay, I'm just telling you all just to give the parameterization. All right, let's just see that what can we do by knowing all this stuff. I want to find the area of the surface of revolution obtained by rotating y equal to x square. Let's just see how the graph will look like if I rotate the line, the curve y equal to x square. Yeah, for the moment, let's see.
Like visually understood what's happening.
Sorry.
Like I understood visually what's happening
Okay.
when you rotate it.
Good. Yeah, I understand. You just help me in finding that. Okay, I know that you understand. Okay, the curve y equal to x square looks like this, right?
Yeah.
And you have a given bound that x is being, it's a certain bound that you are not allowing to go to all the x's, but you have to bound yourself to b. Suppose this is my b. Okay, suppose this is my b. I want to rotate along the x-axis. Can you tell me the figure? How would it look like when I rotate this curve along the x-axis? What would you get?
It would be like a cone, but not a cone. Curve.
Exactly right. It will be like a cone or like a, horn, where we big horn, where we take a horn and then make an head. What do we say? You might have seen in the
Loudspeaker.
loudspeakers. Yeah, that's what. Loudspeaker. It will look like loudspeaker. So when you revolve, it will like this kind of thing. I hope that the figure looks like actually loudspeaker. Okay. Yeah, this should
Yeah.
be okay. Fine. So we have this y equal to x square, and then this region would be y equal to minus x square, right?
Yeah.
Fine. So we have the curve, and then we know the parameterization by the above given parameterization. How to parameterize a revolved surface. So I would just simply write here, just a moment. So the parameterization, if you just see the parameterization, it would be x fx cos theta and then fx sine theta. And here y equal to fx equal to x square. Yeah, this is the graphs. So the revolution coordinates are going to be,
Yeah, this relation is valid when we are rotating around the x-axis.
well, yes, because then only we are fixing x, right? Yeah, you're right. You are right. And there is slight difference here. So there is a slight typo. It should be theta. Theta from 0 to 2 pi. Again here, theta from 0 to 2 pi. All right. So yeah, if we are revolving this, yeah. Otherwise it will be changed like in this way. Suppose you are revolving around y axis, so you will be getting X in terms of function will be X in terms of Y. Then you will write here Fy cos theta, then Y, and then Fy sin theta. Something like that. I mean, it will be just one coordinate you have to fix. Rest of them you can compute by trigonometric functions. Yeah. Okay, so I think this is okay. So then the coordinates will be x square cos theta, x square sin theta. These are my rx theta now. What do we want to find? We want to find the area of the surface. And if you remember, it is nothing but f dot ds over the surface s. This is the like you want to integrate your f over the surface s. Yeah, like you want to integrate, of course there is a curve involved here in order to get the surface integral. So surface integral means you should be able to, you have to see that what is y first of all, and then you have to find ds. Yeah, so here your f is nothing but x square only. This is your f, and x square I will just simply write x square I cap 0 j cap 0 k cap, and then ds, if you remember, it was like rx cross r theta. These are two parameters we have, x and theta, and dx d theta, sorry there is a norm over here, and then over the surface s. Yeah, this was the surface integral we have been doing. Yeah, this is the same formula, right?
Yeah.
Okay, so sorry, this has to be x square only. X square integral over x square time rx is nothing but, I will just quickly write what is this, I cap j cap k cap 1 2x cos theta 2x sin theta 0 minus x square sin theta x square cos theta. So it would turn out that the norm of this, I will directly write the norm, it will be x square times 1 plus 4x square. Okay, I'll just simply write square root 1 plus 4x square times dx d theta, and you know dx d theta limits, d theta is from 0 to 2 pi, and x anyway we know it is from 0 to b. 0 to 2. Yeah, and I think it can be solved. I'll just leave it. Okay, let me just go back what I've been doing. We have been doing finding the surface of a revolution obtained by rotating a surface. That means we are kind of integrating, a surface, sorry, integrating a function given by y equal to x square over the surface which have been obtained by revolving. Now I do not know the surface, right? I do not know the surface, what that is.
Yeah.
The surface has been obtained by rotation, but I don't know how to write that surface. But we know how to parameterize a surface given by certain curve. If I have to revolve a curve and finding a surface, then this is the way. This is the way. I just got the coordinates for the surface. And once I got the coordinates of the parameterized surface, I will use that formula. F dot ds is nothing but the parameterization times dx d theta. And I will just simply compute the integrals, and that would give me the surface integral. Does it make sense?
Yeah.
Okay, so I think I have just done all the things, all the type which I found interesting. I think it should be somewhat helpful. Let's just hope that. Okay, so was that okay? Like, did you understand the concepts?
Mostly, and later I can come back to the recording if necessary.
Yeah, one thing is that. Another thing, you can also go back to the this written notes also. I'll upload the notes. Are you able to access the notes, by the way?
Yet, to the extent that you have uploaded, they are available in the sheet.
Yeah, they are available. Okay, then